Alrighty, good morning everybody. Welcome back to Calc 1. Plan for today is we're going to finish off our discussion of Standard 18, talk a little bit more about finding area approximations using rectangles, kind of building off of last class. And then the second half of class today, we're going to start looking at Standard 19. I've got my usual office hours today at 11 and 2, tomorrow at 10 and 1. And plan is to have a quiz then on Friday over Standard 18. And also don't forget you have a homework set, homework 20, that is due on Friday. Any questions or comments before we get started for today? What do you call a number that can't sit still? You call it a Roman numeral. Man, you all are tired today. Still don't show more energy. I'm going to make you get up and do jumping jacks halfway through class. Okay, so when we left off last time, we had talked sort of about the classical area problem and how to approximate an area. Specifically, he said that if you're given some function f of x, and I think the function we looked at last time was x squared from 1 to 5, so if you want to approximate the area between the function and the x-axis, you can do it by sort of drawing out rectangles and saying, let's say we have a bunch of rectangles whose heights are equal to the values of the function at various points between 1 and 5. And we said that L sub n is going to give us our left endpoint approximation. With n rectangles, where left endpoint means to find the height of each of your rectangles, you would go to the left endpoint of each of the intervals and take the value of the function at that point. Whereas with a right endpoint approximation, you do the same thing, except to find the height of each rectangle, you take the value of the function at the right endpoint of each interval. So looking at this picture here, does that look like a right endpoint approximation or a left endpoint approximation?
Right endpoint.
What's that, Josh?
A right endpoint.
Yeah, it looks like a right endpoint because you take this last rectangle here, the height of the rectangle is equal to the y value of the function, f of x, at the right endpoint of, say, x equals 5. So this would be at like f of 5, this would be at like f of 4, f of 3, f of 2, using the right endpoint of each interval. And if we use the left endpoint instead, we get a left endpoint approximation. Yeah, Josh?
Sorry if this was addressed earlier, but for the quiz, will you have the graph drawn for us, or do we have to draw it ourselves? Assuming it's a problem like this.
If it's a fancy function, anything more fancy than like x squared or a linear function, I will give you a graph. Or alternatively, I will not give you a graph, but then not expect you to necessarily have a drawing to work with. Good question. So we said that in general, the more rectangles you use, the better an approximation we get. And in fact, we said that if you take a limit as n goes to infinity of either r sub n or L sub n, those values are going to get closer and closer to the actual area underneath our curve. So if you look at, let's see, the first, second, third, fourth page of the packet, I kind of go through and talk about how you actually do this process in great detail. So I'm going to go to the next page in the packet, and we're going to look at a new function, g of x equals 25 minus x squared. And I want to approximate the area underneath this from 0 to 4. If we graph out, it's going to look something like this. Tyra, give me a letter, L or R?
L.
All right, so Tyra has proposed that we look at a left endpoint approximation for this region. 2 rectangles or 4 rectangles, do you think?
Let's start with 4.
Okay, so Tyra wants to find L4. So in this region, we're going to split up and do 4 different rectangles, kind of approximate the area underneath our function g of x, which is this upside down parabola. If I kept going, would go like that. From x equals 0 to x equals 4. So let's draw out our 4 rectangles. And here, I'm using the left endpoints of each interval to kind of graph out where the rectangles are going to be. How would we find the width of each of our rectangles? Is it?
Isn't it just 1 because they're each 1 unit wide?
How do you get that they're each 1 unit wide?
It said 0, then 1, 2, 3, 4.
Yeah, so in general, whenever you want to talk about the width of each of your rectangles, which I'm going to call delta x here as being the rectangle width, you can always just take the difference between the endpoints, in this case 4 and 0, and divide by the number of rectangles, n, that you're looking at. In this case would just be 4 minus 0 divided by 4, come out to 1. So yeah, I think I agree with you, Cecilia. I think they're each going to have to be 1 unit wide in order to find our area approximation here. So we have 4 rectangles, which I'll label A1, A2, A3, A4. And if we want to find our L4 area approximation, we're going to need to add together the areas of each of these rectangles. What's going to be the height of our first rectangle? Avery?
F or g of 0.
What do they call this function? I call it g of x. Yeah, I think we would need g of 0. Since we're using a left endpoint approximation, that means at x equals 0, that the height is just going to be the value of the function at the left endpoint of our interval. And so our A1 is going to be the width of the first rectangle times g of 0, the left endpoint of that rectangle. Hannah, what's going to be the height of our second rectangle, A2?
G of 1 is 24.
Yeah, it's going to be g of 1, which, when we calculate that in the next step, is going to come out to 24. Aiden, how about the height of our third rectangle?
G of 3.
It's going to be
G of 2, sorry.
G of 2? I think we are going to have a G of 3, but not quite yet. And Elise, how about our last rectangle height? Yeah, rectangle going from 3 to 4. We're always using the left endpoint for the heights. That'll be G of 3. And the reason why I'm multiplying out 1 times G of 0, 1 times G of 1, 1 times G of 2, etc., is just to make sure that we're not forgetting that we have to multiply each height by the width in order to get the corresponding area of the rectangle. So we take g of 0, that's going to be 25 minus 0 squared. G of 1 is going to be 25 minus 1 squared. G of 2 is going to be 25 minus 2 squared. G of 3 is going to be 25 minus 3 squared, which is going to be 25, 24, I think is, and is that, that square should be just on the 2. 25 minus 4, I think is 21. Yeah. Dr. Gerstle, place your squares in the correct places. And 25 minus 3 squared will be 25 minus 9 is 16. If we add these together, I think it's going to come out to 25 plus 24 is 49, 70. I got 86 as my area approximation. Is L sub 4 in this case going to be an overestimate or an underestimate for the area under our curve? That?
Over,
Why over?
because there's the extra stuff on top of the curve. It's rectangles.
Yeah, it says our rectangles include everything under our curve, plus a little bit extra. These sort of X'd in areas here are kind of our extra area that we're getting by taking our left endpoint approximation. When we did our example with x squared yesterday, did L sub n give us an over or underestimate in that case? Yeah. Give us an underestimate in that case. What gives? So in yesterday's example with x squared, we had a function where our left endpoint approximation gave us an underestimate, and our right endpoint approximation gave us an overestimate. It's going to turn out to be flip-flopped here. L sub n is always going to give us an overestimate, whereas R sub n is always going to give us, spoiler alert, an underestimate. What do you think that is? Danielle?
The curve is going down now instead of up.
Ah, so here our function was increasing as we went from 1 to 5, meaning if we looked at, say, R sub n, the right endpoint was always higher than the left endpoint in each of our rectangles. Whereas over here, our right endpoint is smaller than the left endpoint since our function's going down. What do y'all think? Josh, is that
It is what it is.
I don't know what to make of that response.
It's, well, how we're making our rectangles, where our points are, if the slope's negative, that's just gonna be inverse.
Yeah. It's going to turn out to be the case that L sub 4 here is going to give us an overestimate because f prime of x is negative on the interval we're looking at. Whereas if we look at f of x equals x squared, it's going to be the opposite. L sub n would be an underestimate because f prime is positive, meaning the left endpoint is always smaller than the right endpoint here. Opposite's going to be true for something like 25 minus x squared where our function is going down. Any questions or comments? So there's a few questions on this page that I'll let you all take a look at on your own. Finding L4, L2, R4, R2. One of my favorite things about R2, by the way, from the original Star Wars trilogy is when something would happen to him and he'd give out a little scream like, wow! Oh, God bless that little droid. Let's see. So I'm gonna flip to the back page. When will R sub n give an overestimate versus an underestimate? So where are my? Where is it? So I think what we're going to be able to say in general is that R sub n in general is going to be an overestimate if what has to be true about our function over the interval that we're looking at in order for something like R sub n to give us an overestimate. So if we had a function like this, for instance, how could we kind of sum up what we saw in the previous example and give sort of a condition on our function for when R sub n will necessarily give us an overestimate for the actual area? Rachel?
If f prime is positive.
Yeah, if our function f of x is increasing, i.e. if f prime of x is positive over our interval that we're looking at. If that happens, you know R sub n is always going to give you an overestimate. And we could similarly say that R sub n is going to be an underestimate if what ends up happening. What has to be true in order for our right endpoint approximation to give us an underestimate for the area under the curve? Elise?
F of x has to be decreasing.
Yeah. Or in other words, f prime of x,
F of x is negative.
or f prime of x is negative, exactly. Yeah. If we have a decreasing function, meaning our derivative is negative over some interval, then R sub n will give us an underestimate. And if our function is increasing, meaning f prime is positive, that means any right endpoint approximation will always give us an overestimate. And we can just say vice versa for L sub n. Meaning L sub n is an underestimate if f prime is positive, and L sub n is an overestimate if f prime is negative. So depending on the sign of your derivative, whether your function is increasing or decreasing, you can use that to help you determine if you're going to get something where f of x, where R sub n / L sub n is an over or underestimate for the actual area. So, question. What do you think would happen if we had a function that did something like this? And we were trying to approximate this area with, say, a right endpoint approximation. So here I just drew out a 1, 2, 3, 4, 5, 6, and R sub 6. think that would be an overestimate or an underestimate for the actual area? That,
It'd be pretty close, but it'd be an under.
you think it'd be a bit of an under?
Yeah,
Because you think like, maybe like this region right here?
yeah, it's a bit bigger than the overlapping regions.
Yeah, I would say for something like this is maybe an underestimate? In general, if you have a function that's sometimes increasing, sometimes decreasing though, it's generally pretty hard to say. So if your function's always increasing, then you know R sub n is an overestimate. If your function's always decreasing, over the interval that you're looking at least, you know R sub n is going to be an underestimate. But in general, we can say if f of x is both increasing and decreasing, is increasing over part of the interval, and decreasing elsewhere, then I think we can say we're going to know that overall it's hard to tell whether you have an over or underestimate, and then I think it's just going to depend on the individual function and the individual interval that you're looking at. And it's hard to say if L sub n and R sub n are over versus underestimates. Any questions or comments? All right, that's gonna do it for standard 18. Oh, hold on, please.
Nothing, I'm just surprised. That's all.
You're just surprised what?
We're moving so fast.
I know, time is flying. Just you wait for the next standard. Couple comments on this standard. What can you expect on the quiz on Friday? Probably something like, here's a function f of x, here's an interval from, I don't know, 1 to 10 or something. Find, say, L sub 4. Tell me if L sub 4 is going to be an over or an underestimate. And then you basically have to know that based on, is your function increasing or decreasing over the interval we're looking at? Or if I decide to be a big fat jerk and give you something that's doing a little bit of each, then you probably would just say it's unclear. Yeah, you can probably expect something like that for the quiz on Friday. And yes, Josh, I'm not going to make you have to graph out by hand anything that's in any way complicated. If I want you to have a graph, I will give it to you. Or give you something like, I don't know, x squared that's a pretty simple graph. I'm going to be like, haha, Josh. Sketch out a graph of f of x equals natural log of x plus e to the cosine of x over the interval from 1 to 5, and tell me if that's going to give you L sub 7 is going to be an over or underestimate.
I bet Josh should do it.
Oh, you do think, huh? Well, if Josh can, then the whole class can, so maybe I will give you one. You don't think so?
I won't put it past you.
Huh? I was going to say,
Maybe an M minus.
If I was a betting man.
Zach, shut up before you convince me to give something like that. All right, so we are moving on to standard 19. Ooh, this is one I've been waiting for.
FTC.
What's that?
Team standard.
That's a YouTuber, FTC.
Or,
Oh, these are annoying.
oh, just you wait. All right. Start out. I'm going to tell you all about a mathematician named Gauss. full name. Gauss is a German mathematician, like 1800s. When he was in school as a kid, the legend has it, he was a bit of a show-off know-it-all. He loved to show up his other students in his classes, make them look bad. Kind of student you don't want to be in class with. So his teacher got fed up with him one day, and when he was in 3rd grade or something. And so, legend has it the teacher said to him, "All right, Gauss, you think you're so clever. I want you to add up 1 plus 2 plus 3 plus 4 all the way up to 100. Hoping that would shut Gauss up for a little bit and give the teacher and the other students a little bit of peace of mind. And then, of course, Gauss, as legend has it, figured it out that sum in 20 seconds. So, what did Gauss do? Turns out Gauss did not actually go through and add 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and do that all the way up to 100. Gauss had a trick. And the way the trick worked is to add up all the numbers from integers from 1 to 100. He put the integers from 1 to 50 in a column. And then he put the rest of the integers from 51 to 100 in a column next to the first column. But going upwards instead of downwards. And then instead of adding, going down the column and up one column, the way Gauss figured this out was he added across each row individually. Pietro, what is 1 plus 100?
101.
What is 2 plus 99?
101.
3 plus 98?
101.
49 plus 52?
101.
50 plus 51?
101.
So instead of adding 1 plus 2 plus 3 all the way up to 100, what he did instead was he said, well, it doesn't matter the order in which we add all of these integers together. The order doesn't matter as long as we get all of them in there. So instead of adding across columns, he added across these rows and said that the sum from 1 to 100 of the integers is going to be the same as taking 101 plus 101 plus 101 plus 101 plus 101 plus 101 plus 101 and add 101 to itself 50 times. Once for each row. So that in taking the sum from 1 plus 2 plus 3 all the way up to 100, he was able to make this massive addition problem into a multiplication problem. So here's my question. How could you take 101 plus 101 plus 101 plus 101 added to itself 50 times, and how could we turn that into a multiplication problem? Okay?
101 times 50.
Yeah. We could take it as 101 times 50. Which 100 times 50 is 5,000, 1 times 50 is 50, so 101 times 50 should be 5,050. And boom. That was Gauss's trick for adding up all the integers from 1 to 100 in 20 seconds or something. Say what?
How old is this story true? It was in 3rd grade?
I have no idea if this story is actually true or
okay.
not. It's one of these math legends. Gauss would go on to be one of the most prolific mathematicians of all time. But Did he actually do this when he was in 3rd grade? I mean, I don't know. Just like the story of, did Albert Einstein actually flunk math when he was in like 3rd grade? He may not have, but it makes for a nice story if nothing else. So, where are we going with this? 1 plus 2 plus 3, all the way up to 100. We were able to add by transforming our multiplication, our addition problem to a multiplication problem, where instead of having to do like 99 separate additions, we could just do multiplication once. And truth be told, you could actually do this process with any sum from 1 to n. Where if I gave you a sum of the form 1 plus 2 plus 3 all the way up to some n, what we could do is we could put the numbers, split them up into 2 separate columns in the same way. We'll get 1, 2, 3, all the way down to, n over 2. We can make a second column where we have n over 2 plus 1, all the way up to n minus 2, n minus 1, and n. And Emily, what are we going to get if we add 1 and n together? If we add them? Yeah, we're just going to get 1 plus n. Or, I'm going to choose to write it as n plus 1. All right, Emily, how about if we added 2 to the expression n minus 1?
N plus 1.
3 plus n minus 2?
N plus 1.
How about this last one?
N over 2.
I think we're going to get something like 2n over 2 plus 1, which is just going to simplify down to n plus 1 again. And so we're going to end up with, n over 2 copies of n plus 1 added together. And so we're going to end up getting this nice formula for adding 1 plus 2 plus 3 all the way up to n. It's going to be n times n plus 1, or sorry, it's going to be n over 2 times n plus 1, which you may have seen written before as being n times n plus 1 over 2. And this is a cool trick that no matter what you plug in for n, this is, as long as n is a positive counting number, positive integer, this is going to work. You want to add up all the numbers from 1 to 1,000 really quickly? Take 1,000 times 1,001 and divide by 2. Get something like, I don't know, 500,000 and change. Want to add up all the numbers from 1 to 1,000,000? 1,000,000 times 1,000,001 all over 2. You want to add up all the numbers from 1 to 2? So you know 1 plus 2. 1 times 2 over 2. No wait, sorry. 2 times 3 over 2. Okay. I can add up 1 to 100 in my head, but adding 1 plus 2 is where Dr. Durst will start struggling. Any questions about this formula? So we're actually going to have a couple. There's actually a couple other nice formulas that work similarly. If you want to add up the squares of every integer from 1 up to some value n, you can do that by taking n times n plus 1 times 2n plus 1 all over 6. And if you want, you could even do the same thing with cubes. Get 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. which is going to be n times n plus 1 over 2. Quantity squared. And using this kind of trick that Gauss came up with, you can come up with a lot of nice fun formulas for, I don't know, maybe you don't think they're nice or fun, but I do. My opinion is what matters in this class. You can add up all the integers from 1 to n, all the squared integers from 1 to n squared, all the cubed integers from 1 to n cubed, using some pretty gnarly formulas like this. Any questions or comments about any of these formulas? Dr. Gerstle, where in the heck are you going with this? So remember how in the last standard we were finding area approximations using rectangles for the area underneath the curve? This standard is going to be about how to take those approximations and get exact numbers for the area underneath the curve. So if we flip the page, on the second page of the packet, I'm going to define a new expression for what it means to take the area under a curve from one value of x to another value. And I'm going to define something called the definite integral of the function f of x from x equals a to x equals b, which will denote, using this funky swirly symbol with an a on the bottom and a b above, and that's going to be the exact area under f of x from x equals a to x equals b. And this standard is going to be all about how do we compute this? How do we find the exact area underneath some function between two different values of x? Definite integral. Where have we seen integral, the word integral popping up before? Yes? Yeah, we've seen something called the indefinite integral, which is given an indefinite integral of a function, find all the antiderivatives of that function. Here, we're going to use the word integral in a new context, where here, I want you to think of definite integral, instead of being a collection of antiderivatives, a definite integral, and you can tell if you have a definite integral if you have kind of numbers at the bottom and the top of your integral symbol. Those numbers are going to correspond to saying find the area, so we're going to find a numerical value for the area underneath our function f of x from x equals a to x equals b. So let's do an example. And I want to go back to Josh's favorite example from yesterday, when he wanted to know why are we using these numbers. Let's look at f of x equals x squared from x equals 1 to x equals 5 again. No, we're not doing that yet. So I want to find the exact area underneath this curve, f of x, from 1 to 5. And this time, I don't want to just say, oh, it's an approximated area. Our engineer has left the class for today, Joseph, but he was unhappy yesterday when we were just saying things like, oh, the area has to be between, I don't know, like 30 and 60 or whatever. He wanted to get some more exact numbers. today we're ready to do it. We're gonna find the exact number for the area underneath this curve. So we know how to approximate the area under this curve. This would be like what the area looks like using 4 rectangles. Danielle, how did we, given like an area approximation using something like 2 or 4 rectangles, how did we say last class that we could take this approximation and make it more accurate by doing something slightly differently?
I just remember you said add more rectangles.
Add more rectangles, yeah. And we said last class that the more rectangles you have, the closer an approximation you're going to get. So if I wanted to use a bunch of rectangles, we're going to stick to the curve more and more closely and kind of have less, if we're doing, say, an R sub n, it's going to have less overhang. And in fact, we said last time that the actual area is going to be what we would get if we take a limit as n goes to infinity of R sub n. Or in other words, a limit as n goes to infinity of L sub n, meaning as the number of rectangles you use gets bigger and bigger and bigger, the right and left endpoint approximations you get using that number of rectangles is going to get closer and closer and closer to the actual area underneath the curve. So what I want to do today is, instead of finding R sub 2 and R sub 4 and all of that, we're going to find a formula for R sub n and take a limit of that as n goes to infinity. Get an exact value for our area underneath the curve. So I'm going to write this as the definite integral of x squared from x equals 1 to x equals 5, which according to this notation just means find the area underneath f of x from 1 to 5 exactly. And the way we're going to do that is we're going to find an expression for R sub n using n rectangles and take a limit as n goes to infinity. Meaning we're going to need a limit as n goes to infinity of taking the area of some a1, our first rectangle, plus a2, plus a3, all the way up to a sub n. So question, if we're using n rectangles, and we're splitting up the interval from x equals 1 to x equals 5 into n rectangles, how wide are each of our rectangles going to be? In other words, if we wanted to cut up the interval from 1 to 5 into n equally sized pieces, how wide are each of those pieces going to have to be? Elise?
4 divided by n.
Yeah. It's going to be the length of the interval, and I'm going to call this delta x, which was our notation for the width of our rectangles. That's going to be 5 minus 1 divided by n. It's going to be the length of the interval divided by the number of rectangles, which in this case is going to be 4 over n. And so I would say that the width of the first rectangle is going to be 4 over n. The height of the first rectangle is going to be 1 plus, well, if the first rectangle is going to go to from 1 to 1 plus that width, so 1 plus 4 over n, since we're using a right endpoint approximation, the height of that rectangle is going to be f of 1 plus 4 over n. And then we can repeat. Our second rectangle is still gonna have a width of 4 over n. It's gonna have a height of, oh, let's see. Our first rectangle goes from 1 to 1 plus 4 over n. Second rectangle is gonna go from 1 plus 4 over n to 1 plus 4 over n plus 4 over n, which is gonna be 1 plus 8 over n. And then, turns out we can repeat this process all the way up to our last rectangle, which is going to be, still have a width of 4 over n, and it's going to have a height of f of 1 plus 4 times n over n, because it's the nth rectangle, meaning we've started at 1, and we've traveled out 4 over n times to get to our last endpoint. So it'll have so the last endpoint is going to be at 1 plus 4n over n, which, as you all probably know, is just going to simplify to 1 plus 4 is 5. All right. So now, is there some term that we can factor out from all of these? I look at each of these n different expressions for area, and I see something that each of these has in common. What do all these terms have in common, Josh?
4 over n.
Yeah, we can pull out a factor of 4 over n. I'm going to say this is all equal to 4 over n times, and then we can plug in f of 1 plus 4 over n, which will just be 1 plus 4 over n quantity squared. This will give us a 1 plus 8 over n quantity squared. This is going to give us a 1 plus 4n over n quantity squared. And all of these are going to be multiplied by 4 over n. And then we're going to take the limit of this expression as n goes to infinity. What's up, Josh?
Where are you getting the squared from? Oh yeah, f of x, sorry.
Yeah. So this one is specific to the function f of x equals x squared. F of thing is always just going to be thing squared. Rachel?
For the second one, how did you get 8 over n?
How did I get like that this one went from 1 plus 4 over n to 1 plus 8 over n? Well, it was because, let's write this out over here. No, let's write this out over here. So we have an interval from length of going from 1 to 5, right? And we're splitting this up into chunks, which Elise said are each going to have a width of 4 over n. So if we start at 1 and go out one chunk of length width 4 over n, that's going to take us to 1 plus 4 over n, yeah? What would happen if we went to another copy of 4 over n, meaning we went out another rectangle in our interval? What would this endpoint be at? If our rectangle starts at 1 plus 4 over n, and we've gone out another copy of 4
So
over
it's
n.
like 2 4 over n.
Yeah, it's going to be at 1 plus 4 over n plus 4 over n, which is where this 1 plus 8 over n term is coming from. All right. So now, I don't think we have a choice in the matter. We need to actually FOIL each of these out. I can hear everybody shouting in glee. All right, so this will give us 1 plus 4 over n plus 8 over n plus 16 over n squared when we factor this term out. Similarly, if we multiply the second one out, we'll get a 1, we'll get a 16 over n, we'll get a 64 over n squared. And then if we keep going, our last term will have a 1 plus 8n over n plus a 16n squared divided by n squared for the width of our last rectangle. So in other words, this expression evaluates out to that.
explain the 8n one more time?
How do we know that our second rectangle has a height of f of 1 plus 8 over n? Yeah. So basically, it comes out to the fact that all our first rectangle starts at 1, and each of our rectangles is going to have a width of 4 over n. So to get to the endpoint, right endpoint of our first rectangle, we have to add a single copy of 4 over n from our starting point to kind of get what's the x-coordinate of the end of the first rectangle. And then to get to the endpoint of our second rectangle, we're going to get 1 plus 4 over n. We're going to have to add 4 over n again a second time, which is where the plus 8 over n came from. All right. Each of these underlined expressions has a term in common. Like these three terms has something in common with these three terms, has something in common with these three terms. What do each of these three underlined segments all have in common? Rachel? They all have a copy of 1 in common. So I'm going to regroup all these terms and just kind of combine all the copies of 1 out at the start. So at the start, we're going to end up with n different copies of just plain old-fashioned 1. And then I'm going to take the second term of each of these, the 8 over n, the 16 over n, all the way up to the 8n over n, which is going to give us an 8 over n plus 16 over n. They'll give us like 24 over n, all the way up to an 8 times n over n. And finally, I'm going to take the last term of each of these underlined terms. A 16 over n squared, a 64 divided by n squared, all the way up to 16n squared divided by n squared. All of these being multiplied by 4 over n, all of these taking the limit as n goes to infinity. I think you're starting to see why this is one of my favorite standards. All right. I'm going to limit as n goes to infinity of 4 over n times Ellen. If I were to add 1 plus 1 plus 1 plus 1, if I were to add 1 to itself and with n copies of 1, what is that sum going to come out to?
It would just be 1 times that.
Yeah. If we're adding 1 to itself n times, that's just going to come out to 1 times n, or n. So this term is going to simplify down to a copy of n. This term, eq, I don't know how to simplify that one. But I do know that I can factor out an 8 over n from that term to get an 8 over n times 1 plus 2 plus all the way up to n. Basically saying this term right here, if we factored out an 8 over n, the first term would be left with just a 1. The 16 over n, if we factored out 8 over n, would have a 2. And 8n over n, if we factored out an n, we'd just be left with n. Similarly, over here, if we factored out a 16 over n squared, what we're going to be left with is 1 squared plus 2 squared, all the way up to n squared. And now, we're going to go use that tangent we went off for a little bit about how Gauss was a smart aleck in class. going to be 4 over n times n plus 8 over n. What's the sum of 1 plus 2 plus 3 all the way up to n? We found that on the front page. This sum right here turned out to just be n times n plus 1 over 2. Using that Gauss's trick, adding up in the columns on the front page. And similarly, this 1 squared plus 2 squared plus all the way up to n squared, whatever n is just going to come out to n times n plus 1 times 2n plus 1 all over 6. And now, if we take the limit as n goes to infinity of all this stuff, I'm going to multiply I'm going to multiply the 4 over n now by each of these terms separately. In other words, I'm going to distribute the 4 over n out to each of these. And when we do that, we're going to get a limit as n goes to infinity of 4n divided by n plus 32 divided by n squared times n plus 1 over 2 plus 64 over n cubed times n plus 1 times 2n plus 1 all over 6. As n goes to infinity, 4n over n is just going to go to 4. This term right here is going to go to 32 divided by 2. Why does that go to 32 over 2? If you factor this all out, take a limit as n goes to infinity, you can do some fancy standard 2 algebra, which we'll address at the end of this problem. But for now, just trust me, this comes out to 32 over 2. I would not lie. It's hard to tell, but I'm trying to get an evil grin behind my mask. This expression is going to come out to 128 over 6 if we take a limit as n goes to infinity. And it's going to come out to 4 plus 16 plus 64 thirds, which will give us 20 plus, what's that, 21 and a third. Boom! We just calculated the area underneath the graph of f of x equals x squared from 1 to 5 exactly. Not just an approximation, but exactly. So to sum up, we found the actual area by looking at a right endpoint approximation with n rectangles and taking a limit as n goes to infinity, which means taking a limit as n goes to infinity of what's the area of the first, plus the second, plus the third, all the way up to the nth rectangle, which we did a lot of algebra gobbledygook to get to here. We used Gauss's formulas to simplify 1 plus 2 plus 3 all the way up to n, 1 squared plus 2 squared plus 3 squared all the way up to n squared. And then we did a bunch of, well, I did behind the scenes, a bunch of standard 2 stuff to simplify each of these limits down to get a numerical answer of 41 and a third for the area under x squared from 1 to 5. Emily, you look like you're about to puke. All right, you want to know why this is arguably my favorite standard of the semester in actuality? It's because the actual standard 19, you are not going to have to do any of this. This entire second half of class today was a giant trick. Where I've tricked you into thinking you would have to do this for the standard, 19, when in fact standard 19 is centered around something else entirely. You've been deceived because A, I like to see you suffer, and B, I think it's good for you to see what this process would look like if we didn't have a nice trick for actually being able to compute this much, much, much more easily. By the way, this function, you see how horribly nasty all of this computation was? This was just computing the area under x squared. If I had given you something like f of x equals, I don't know, cosine of x plus e to the x minus x cubed over 17x square root of x, which by the end of this standard you all will be prepared to handle. Can you imagine how nasty this computation would have been for a function like that? Josh, the more you say, you don't need to really get Josh and Zach kicked out of the class. Because every time they make comments about how easy something looks, or it makes me want to force you to have to go through this process for something like that function.
I believe Josh should do it.
You figured it out. This is all you this time.
I think it's all you, man.
Yeah, have fun with that.
Get there, cowboy.
I don't think I could do that one, so good luck for the two of you. Okay, I actually think that's a good stopping point for today. I want you to see the hard way of doing this, so that when you see the easier way in class on Friday, you can appreciate how much less work it is and how awesome this our next theorem is going to be for helping us to compute areas a lot more simply.
Tell Joe. Yeah. Tell him we have a double quiz. Show him.
Yeah.
Double quiz and show me that? You're on. All right, hope y'all have a good rest of your day. I will see you all on Friday. Don't forget, on Friday, we're going to have a standard 18 quiz. And on the standard 18 quiz, I'm not going to say compute, do all this. It's just going to be a compute something like R4 or L2 or something like we did in the previous packet. And then be prepared to talk about if it's over or under. Have a good one, and I will see y'all on Friday. Standard 17 retest? Yes. Send me an email to remind me, and that should be fun. Have a good one, right?
You too.